You can think of pre-calculus as being math without limits and calculus as math with limits. So clearly coming to terms with limits will be very important to us. It will take a little while to get a good understanding of what limits are really for and why they're so important to us in calculus. I'll try to give you a hint now as to why limits might be of interest to us. We're used to using formulas to build graphs. However, there are often certain kinds of information about the graphs or that is difficult to derive directly from the original formula. Each time we use such a formula, we get information about only one point and no information about what's happening near that point on the graph. Here's an example of what I'm talking about. Consider the function y equal f of x equal to x squared minus x. If I want to know about the point at x equal to 2, I can plug into this formula and get the y coordinate of the corresponding point on the graph. I'm going to claim that my graph is reasonably accurate in showing that the graph is rising rather quickly as it goes from left to right up through the point 2, 2. However, without calculus, it is surprisingly tricky to verify this in any direct way. But all you can do is plot some nearby points using your formula. Now, these are admittedly not such nearby points, but no matter how close the points are chosen, we really can't say much of anything about what's happening in between them. For all we really know, something like this could happen. Getting our information about the graph one point at a time can be pretty tedious. Limits will ultimately provide us a way of accessing this sort of information directly. We will soon see that limits will give us a way of understanding graphs of functions that have discontinuities, that is, breaks in them. Here's an example of a function that has a rather striking and interesting discontinuity. To analyze this, we are going to be dependent on my graph, at least for now. Notice that we can't plug 2 into this formula because we can't divide by 0. Hence, there's not even a point on this graph at x equal to 2. There is quite a bit of action, though, in the vicinity of x equal to 2. The half of the graph that is to the right of 2 leads right up to the point 2, 3. The other half of the graph to the left of 2 leads right up to the point 2, 1. Limits will give us a direct way of talking about and calculating information like this. Now we're really ready to get to work. This x arrow 2 notation can be interpreted as meaning, and I'll have to explain this, that x is getting closer and closer to 2. One might also say that x approaches 2. We tend to think of the variable x as representing any number that we might want to work with. Here, with the x arrow 2, I think it's easiest to think of it as representing a kind of list of numbers, where as you work your way down the list of numbers, these numbers should be getting closer and closer to 2. And in fact, no matter how close somebody might say these numbers should get to 2, it should be possible to go far enough down the list so that all the remaining numbers in that list are at least that close to 2. Lots of such lists are possible. Here are some more sample lists. For each list, if you go out far enough in the list, one can clearly make the numbers in the list as close to 2 as anybody might possibly want. Now, if you already have, for example, an x approaches 2 list, this original list can be used to build other lists. For example, a list where we add 2 to each number in the original list. Here's an example of a possible x approaches 2 list and a corresponding list x plus 2 built out of it. Here it is clear that if the original list of x's are getting closer and closer to 2, then the corresponding list made by adding 2's to each x has to be getting closer and closer to 4. Or similarly, given that we already have an x approaches 2 list, we might use the formula 3x plus 1 in order to build a new list. If the x's are getting closer and closer to 2, then the 3x's should be getting closer and closer to 6, and the 3x plus 1's should be getting closer and closer to 7. Or if we want another example, if the x's are approaching 2, we can make a list of the form x squared plus 3. We can see that that should approach 7 also. You might be a little bit disappointed to notice that in order to get our limit value, we're still just essentially plugging into the formula. We're now able to talk about limits using the textbook's notation. All right, here's a limit statement. If we have an x approaches 2 list, then the corresponding x cubed minus 4 list is going to have to approach 4. There's a little additional requirement about the x approaches 2 list that every number in that list is going to be something different from 2. In the textbook, they would make this statement using the following notation. In mathematical English, this statement would be read as the limit as x approaches 2 of the function f of x equal to x cubed minus 4 is equal to 4. You'll notice that to this point, we've been plugging into the given formula in order to get our limit value. This is because most routine algebraic functions are going to be continuous. That is, if you look at their graphs, there won't be any breaks in the graph. Generally, if we have a function and a number a, so that at x equal to a, the function has a point, then we would say that the function is continuous at x equal to a if the following formula holds. This says that in order to find the limit value of f at x equal to a, we just plug a into the formula. You should think about what this says, and in particular, think about why this is saying that the graph of f can't have a break in it at x equal to a. Here's a quick example. If we want to find the limit value for the limit as x approaches 3 of the function f of x equal 4x minus 1, then all we're going to have to do is plug in 3 in place of x and see that we're going to get 12 minus 1 or 11. If the function that you're working with is known to have a continuous unbroken graph, then there's no way that you can get into trouble just plugging in. Here I can find the limit as x approaches 9 by just plugging in 9 to get the limit value of 2. We know that sine of x has a nice unbroken graph, so we can form limits using sine by just plugging in just as before. We wouldn't care about limits if all we ever did was plug into the formula that gives us the graph. So we should get busy and find ourselves an example where we can't just plug in. So here's one. A function like f of x equal to x squared minus 9 divided by x minus 3 is an obvious candidate for being a possible troublemaker. And that's because we see that it's possible to be dividing by 0 if we plug the wrong number in for x. The limit value is certainly not f of 3 because f of 3 doesn't even exist. If we have a graph in front of us, then we're in a much better position to compute the limit as x approaches 3. So let's look at the limit as x approaches 3 by looking at the graph. If we look at x is approaching 3, say from the positive side, here are some x's on the positive side of 3. Corresponding points are up here above, and clearly they're getting closer and closer to the missing point that is at the point x equal to 3, y equal to 6. The function values are the y coordinates of these points over here, and clearly those y coordinates are getting closer and closer to 6. It could be rather tedious to build a graph like this. We would like to have a method that would allow us to compute more directly. So here's the question. It turns out that it's really not too difficult, at least when we're looking at functions that are made out of a fraction involving polynomials, to actually directly compute such a limit. Okay, let's take a closer look at the function that we're trying to take the limit of. We should notice that when we try to plug in x equal to 3, that we get a 0 in both the numerator and in the denominator. This should catch our attention, because if you can plug a number into a polynomial and you get 0, then that means that that polynomial factors with x minus that number. Let's exploit that here. Both numerator and denominator factor with an x minus 3. This will allow us to reduce. Notice that y equal to x plus 3 is the same line that we had graphed earlier, but now we have the formula for a function that is continuous, and we no longer have any problems with plugging in to finally get our answer.